Good morning. First, I would like to emphasize that I'm not a mathematician, but a theoretical physicist. And I also have not worked directly on Monstrous Moonshine, but around 2008, I was doing my own business, which was counting some stuff. And out of the blue, the Modular Group M24 appeared in my calculation. And today that's called Monstrous Moonshine, and there's a much larger story which mathematicians are studying called umbral moonshine. But these lectures are going to be stuff I picked up for fun, but there's also, I'm a string theorist by training, so we do conformal field theory, and a lot of things, ideas from conformal field theory come in Monstrous Moonshine. And except there's a problem of language, and mathematician physicists describe the same things in slightly different words. So it makes my job a little hard, and please forgive me if I say something wrong, and please feel free to correct my wrong mathematical statements. Okay, so I'm going to start with the story, and mathematicians are specialists, and if you work in group theory, you don't look at number theory, while physicists are generalists. We know nothing, so we go and do everything. So, so first, what is moonshine? And so the normal English thing is the second one. It's nonsense and silly talk, and maybe my 2 lectures will be that. And but in the US, there was prohibition, and so people used to do illegal liquor. We know that in India because that happens all the time. We call it hooch, but the Americans call it moonshine. So, but there's a nice definition of Barchard's, which I'll read. It says that moonshine is not a well-defined term, but everyone in the area recognizes it when they see it. Roughly speaking, it means weird connections between modular forms and sporadic simple groups. You can also extend it to include infinite dimensional Lie algebras, complex hyperbolic reflection groups. And also, it should be something weird and special. There should not be infinite number of examples. There should be only finite number of them. Okay, and my corollary to this is you do not work on moonshine, moonshine finds you. Okay, so there's going to be some lectures on the monster, and you will see that it's a fairly big group, and for physicists, a large number is the number of molecules in a 1 liter of a gas. It's called a mole. It's 10 power 23, but the size of the monster beats it. It's 10 power 53. So it's a really large number. And Monstrous Moonshine is the connection of the monster with a modular function of a group called PSL2Z called the j-invariant. So we'll see, just to give the observation. So there's this function, j of tau. It has a expansion. Q is supposed to be e power 2 pi I tau in many situations, but in this context, people just use Q and act as if it's some formal power series. So you can think of it as a formal power series. And so Mackay was, so this is a case of a guy working in group theory, looking at something which he has nothing to do about with or whatever, and he notices that this term, so look at the coefficient of Q here. It's 1 plus the smallest irreducible representation of the monster. And it's debated whether he also saw the second one. Second one is also a sum of 2 representations, and this large number is the second largest representation of the monster. And so this is Mackay's observation. And Thompson observed this and said, there maybe, is there an infinite dimensional monster module which has this kind of structure? And these H's are called the head representations, such that the dimension of H is a coefficient of Q power M in this series. Okay, I'm using the symbol H here. Later I will shift to V with a shift in M. It will start from 0 here. M starts from -1. And here Thompson also checked that this was true for the next, that he could do the decomposition up to Q power 5. So the plan of these lectures is to sort of understand these things. And the first lecture will be on modular forms, because that's not something which people working in group theory know about. But let me tell you, I mean, it has a lot of similarity to computational group theory in the sense that people working in this area get their hands really dirty. They are doing explicit numbers. And if you're Don Zagier, he can reel out the first 20 coefficients of just about every modular form. He has it in his head. Okay, so the thing is that, so we will discuss modular forms, and then we'll understand what this j-invariant is, and we'll end this lecture with what is called the Moonshine conjectures, and there are 2 conjectures. And my second lecture will basically be on the first conjecture, which is just a statement that there is such a module. Okay, and so let's start with the sort of a quick introduction to modular forms. So let H represent the upper half complex plane. That means tau. Tau belongs to complex numbers such that the imaginary part of tau is greater than 0. And so let's for a moment take this action of SL2R, not SL2Z, like right there. SL2R maps the upper half plane to itself. If you think of the full complex plane with a point at infinity, what it does is it maps the real line to itself and the lower half plane to itself. So the SL2R preserves the upper half complex plane. But now you look at this discrete PSL2Z, where you put in the additional condition that A, B, C, and D are integers. Okay, so this is the transformation, and this group, we'll call it gamma. Sometimes gamma subscript 1 is written. 1 means genus 1 or whatever, because there are other generalizations. But in this lecture, we'll not see that. Gamma is generated by 2 simple transformations. One is called the T, which takes tau, goes to tau plus 1, and S, which takes tau to minus 1 upon tau. Okay, so let's see what T does. So what we have done here is this horizontal vertical lines, this at minus half and translates of minus half by 1. So if you look under T, what it does is it takes a point here to outside here, and of course, this boundary here is identified with this boundary. Okay, so you get a strip. Then let's ask what S does. So draw a circle now, or a semicircle of radius 1, centered at the origin here. It takes points inside the circle to outside this thing, which you can work out explicitly. So one talks about a fundamental domain. That means you want a set of points tau, which under the action of SL2Z will go out of the domain. And so this marked area is one such fundamental domain, and there are identifications. This point, this is identified with this, and this part of the circle is identified with this. So what you have to do is to put it together. It becomes like a cylinder, and then you put that other part, and then it looks like a sphere with a puncture removed, topologically that is. Okay, so this is the picture, geometrical picture of the fundamental domain. Okay, so one also considers subgroups of the modular group, and one defines gamma n to be, so recall that we were looking at matrices where A, B, C, and D are integers. Gamma n is the group and it's a normal subgroup of gamma, as you can check. And any subgroup of gamma that contains gamma n is called a congruent subgroup at level n. So if you say that there is a congruence group at level n, you know that it contains gamma of n. It's not complete information, but it gives you something. One example which we will encounter is gamma 0, 1, which has a weaker condition than this, just says that C is 0 mod n. Okay, so that's so this is this thing. So the next group is not a subgroup of gamma 1, but it's a group which is called gamma 0 n plus. That means it is something which you start from gamma 0, 1 and extend it, and it is given by the normalizer of gamma 0 n in SL2R. Okay? So, and I think this is a beautiful gap exercise in gap probably to ask what this group is. But there is one element which is of interest, which is given by this matrix, which is, I mean, this is just to make it determinant 1. It's 0, minus 1, and 0. And that, what it does is it takes tau to minus 1 upon n tau. If n equals to 1, it is just the S. So in some sense, F1 is S, okay? But there's an interesting this thing for prime P, when n is a prime number, gamma 0 P plus is just generated by gamma 0 P and the Fricke involution. Okay? And this is also known to be a discrete subgroup of SL2. So these are the groups which we will encounter. And so now we will simplify life and we'll talk about modular forms of gamma. So we begin with a function. Yeah. Only for prime P, I know the answer. It's 2, because Fricke involution is an involution. So in that case, I know the index. Other cases, I don't know the answer. 2, because it's generated by gamma 0 n and just this Fricke involution. Okay, so it has this property. Looks a little bit weird, but I mean, you would have liked to look at functions. That means things which are invariant under a transformation of this kind. You would like A tau plus B plus C tau plus D equal to F of tau. But what you will see is that if you put in certain conditions, the only solution to that is the constant, which is a little boring, if you wish. And so what you do is you put an additional factor here, C tau by D power K, and this K is called the weight of this holomorphic function. Okay, and just looking through this, so we can take the special transformation T, which takes tau to tau plus 1, and if you, this implies, so in that case, C is 0 and D is 1, so this factor is gone. So it's like a function, but it is a translation invariant, so it's a periodic function with period 1, and that sort of says, if you think of Q as, so again, remember, one more caution is that there are different notations for Q. Some, I mean, this is most common, but some people use e power pi tau. So then in those cases, t plus 1 will look like t plus 2. So you have to be careful when you're looking at books, when they're giving Q series, what is their this thing. So this just says that you will have this, there will be a Q series with n belonging to Z. But now we'll put some additional conditions and 3 different classes of conditions. If f of tau is bounded as im tau tends to infinity, and so the point here is that you have a fundamental domain, and this is, so if you, this is identified with this, and this part is identified with this. So it's topologically like a tube with this thing. So this point, you give some behavior at this point, or equivalently, you can compactify it into topologically sphere by adding that point. So you just give its behavior there and put and holomorphy takes care of the rest of the story. So if you require that it be bounded as it goes there, then what it says is that, so the key point to remember here is that im tau tending to infinity is just saying Q equal to 0. So if you're, what you want, if your function is bounded, that will require all the negative modes to go away. Okay, so it just becomes, so an should be 0, and then we say it's f is a holomorphic modular form of weight k. If f goes as order q power minus n, that means for this kind, I think it should be q power n, it should vanish faster than this thing for some integer. So this is a typo, it should be plus n. Rather than O1, which is, this is what they're saying is constant, then A of 0 will be 0, and you'll call it a cusp form. Okay? And sometimes you want to let it be meromorphic, if you wish, at infinity. And then you permit the Fourier coefficients to start from some negative value, and you call them weakly holomorphic modular forms. So we have three kinds of objects: holomorphic modular forms of weight k, cusp forms, and weakly holomorphic modular forms. Okay. So let mk of gamma denote the vector space of holomorphic modular forms of weight k. Similarly, we can define sk and mk with an exclamation for the three kind of spaces, and it's easy to see that they sit inside each other. Okay? And a very practical and important fact is that mk of gamma is finite dimensional. We will see how to construct it later. And we can also replace gamma by subgroups such as gamma 0, 1, and again similar considerations will hold. There are more technicalities, there are more cusps in the sense like the analog of these points, point m tau going to 0, there are more cusps, but that's not something I want to discuss today. But now what we're going to do is we'll address, so I told you it's finite dimensional. What can we say about the dimensions of mk of gamma, and we will construct a basis for it. Okay, so again, I'm not going to give you proofs. The proofs you can open any number theory book. I'll also give some references along with the tutorial that I have, and from there you can prove it. So what we're going to do now is to start with examples. And the first example is what's called the Eisenstein series, and let k greater than 2 be an even integer, and you consider this sum. And so first thing is, let's look at why I wanted it greater than 2. For k greater than 2, it's absolutely convergent, so the series is good. And but if k equal to 2, it's not absolutely convergent. And for k less than 2, it's not convergent. Okay, so, and the restriction to even is that if you look at the way the summation is, it's taking over all points, integral points on the plane, deleting 0, 0, the origin. Okay, so, and this prefactor is just put in. This is, some books do not have this, but next formulae become quite nice when you put this in here. And so, and the easy exercise is just 2 minutes to show that this is a modular form of weight k. Nothing, no work needed. Okay, but more involved and obviously more fun computation, which sadly I'm not going to do, shows that, I mean, from our first thing, we know from the definition that there has to be a Q series. Okay, so there are 2-3 ways of doing it, and at least I know 2 ways. And you can show that it has a Q series. And so this zeta of 1 minus k, you can write it in terms of Bernoulli numbers. And this guy is just the divisor function. So, so this has a nice explicit formula. Okay, so here we have an infinite class of examples of what do you call modular forms of even weight. So we got for 4, 6, 8, 10, 12, so on and so forth. Okay, and but in this form we had convergence issues for 2, but in this form we can actually go ahead and put 2. Put k equal to 2 and take that as the definition on the right hand side. And then an interesting thing happens is that this is almost a modular form. And again, that's a nice computation. If you like an analysis, you can use what's called Hecke's trick and show that there is, if you add this guy, so this is imaginary part of tau with this thing, G2 star is not holomorphic, obviously, in tau, but it's a weight 2 modular form. Okay? So this, what it says is that G2 is almost a modular form. Okay? And there's another notation for the same thing, which is EK, which says that you want, so if you look at this Q series, a constant coefficient is some zeta of 1 minus k, so you divide that out so that you get the constant coefficient to be 1, and the standard notation for that is to use EK. So EK and GK are really the same up to an overall scaling. And another factor is all coefficients here are rational. Okay. So let's look at, like I said, the number theorists also like to be explicit. So let's look at E4. And maybe I would recommend remembering only the first terms for at least the rest of this lecture. E4 is 1 plus 240 plus order q square. E6 is 1 minus 504. Maybe I can write it here. Okay. And just notice here that the coefficient of E8 is 2 times 240. Okay, that's what is needed. Maybe that's already here. Okay, so here is so these are examples, and in some sense we are done. We know all modular forms of the full modular group gamma because of this proposition. The ring of holomorphic modular forms. By the way, obvious properties is that if you have 2 modular forms of weight k, you can add them. That's how it's a vector space. But we can do another operation, which is to take two modular forms of weight k, k1 and k2. Their product will be a modular form of k1 plus weight k1 plus k2. Okay. So the ring of holomorphic modular forms. So we'll define M star to be formally the direct sum of all these vector spaces. Okay, and it's freely generated by 2 guys, E4 and E6. So it says if you know E4 and E6, the rest of them should follow. So now let's look at this. Let's look at E8. So E8 is given out here. So, but what it says is E4 square is also weight 8, and the key point is all these guys are normalized to 1. So E4 square, its constant coefficient will, or any product of E's, their constant coefficient will be 1. So that's a reason to work with E's. So we can see that E8. So it has to happen that E8 better be E4 square, because that's the only guy. So another way of saying this is that if you ask what is the dimension of M8, it is 1, and it is generated by E4 square. So E8 must be proportional to E4 square. But both of them have constant coefficient 1, so that coefficient has to be 1. So it's an equality. But it's amazing. Here we only just did this, so and we can check this is true, but actually it is true in full generality. Similarly, let's go to dimension 10. Again, dimension 10, there's only one combination, E4 and E6, which can give this thing. Again, that has to equal E10. I've not given you the formula for E10, but it's easy to check. So the fun begins when we go to weight 12. So weight 12, there are 2 possibilities, E4 cubed and E6 squared. So the dimension is 2, and now if you tell me that, look, I have constructed for you a modular form of weight 12, that better be some linear combination of these 2 guys. Okay. So that is the first class of modular forms, but we will see 2 more constructions, and the next one is something called the Dedekind eta function. And I'm just giving a definition, and eta of tau is that's an important q power 124 times the product of 1 minus q power m. So if without this factor, the inverse of this is Euler's generating function of partitions of integers. In case you've seen that thing, but you need this factor here to make it a more. Okay, so it is a modular form of weight half of a subgroup of gamma, and describing that is a little bit a pain. Proving that is real nice analysis. Apostles' book maybe on modular forms might be a nice thing to look at it. But one thing we can see easily is that if you take t and take t to t plus 1, because there's a q power 1 by 24, there's going to be a phase which is a primitive 24th root of unity. Okay? So, so what we can see is that if I take the 24th power, at least it'll be nice under t transformations, but actually it'll be nice even under S. Okay, I'm not proving that. So let's define the discriminant function. And this name discriminant comes from the fact that it is related to elliptic curves, And we will see this formula here is related to the discriminant of a particular of elliptic curves. So delta of tau is eta of tau power 24, and its expansion starts with a q because this q power 1 by 24 becomes a q. So you get a q series starting with q, and so it's an example of a cusp form. So what we learn is that the first cusp form which we will get for the full modular group occurs at dimension at weight 12. Okay, and again, this should be this should be expressible in terms of these two guys, and a simple calculation shows again that delta of tau is actually this thing divided by 1728. Interesting number. If you add 1 to it, it's the famous cab number of Ramanujan. Okay. So delta of tau actually does a little bit more. It provides an isomorphism between the space of cusp forms of weight k and the cusp forms and just holomorphic modular forms of weight k minus 12. Okay, and how do you see that? You give me some. If you give me a cusp form of weight k, and then if you just divide by delta, you get mk minus 12. Now you may ask, oh, can I divide by delta? And the answer is yes. And the reason is that you can ask where are the zeros of eta. It's easy to see here, but there's a little bit of you have to worry about issues. But you can see here that the zeros of this guy occur only on rational when q is some root of unity. That's when it happens, and those points are all under the SL2Z transformations can be mapped to I infinity. So what it says is that inside in the fundamental domain, delta is nice, and yeah. So here, no, I write q. So yes, that is defined for me. I just define it so. So it's just definition here. Okay, so I'm choosing a particular branch. One second. Yeah, the point is that in fact there are lots of issues when we talk of when we have a situation with weight half, because if you look at the modular transformation, it has the square root of c tau plus d. So you have to tell me actually what is the branch you're going to pick up, and what you do is you go to a double cover, and it's a metaplectic group, and really it's a modular form of that. So in other words, you keep track of the signs. So there are lots of sign issues when you do those things, but all this life is, that's why I'm quickly focusing on delta. Okay. So then there's also another, why would we look at this thing? For instance, here's a product, eta of tau power 8, eta of 2 tau power 8. The combinations like this can be used to construct other examples for modular forms of subgroups of gamma. So for instance, this is one of the generators. It's a cusp form of gamma 0, 2. Okay. So we are ready now to discuss the j-invariant. So you look at the j-invariant, it fits what we will call a weakly holomorphic modular function. It's a function because weight is 0. So when we call something a modular function, we mean weight 0. It's invariant under the full modular group. So if you just go ahead and multiply it by delta of tau, delta of tau is a cusp form. So what the product of these two guys is, the series will start with a constant coefficient. Indeed, the constant coefficient is 1 plus 740q. Okay, and what is the dimension of this? Okay, so let's say this is so this guy is weight 0 and this guy is weight 12. So we'll end up getting something which probably, okay, is in M12. Okay, so again 240. So we can just at that dimension dimension is 2. So we need two numbers to check, and I have those two numbers. So I can actually completely determine the rest of the Q series of this product, and that's just E4 cubed. Okay? And so we obtain a beautiful formula which says j of tau equal to E4 cubed by delta of tau. Okay? So now, I mean, so it's quite interesting that just the first few terms in this function completely and modularity, the fact that it's a modular function, completely determined. J function actually provides an isomorphism between the fundamental domain and C. Okay, so it gets a one-to-one mapping. So so there's some, I need a technical term called Hauptmodul. So first thing is, I already pointed this out, that if you compactify the fundamental domain by adding a point at infinity, it's a sphere. So topologically, it has genus 0, or you can think of this as a genus 0 with one point. Okay. Yeah. So let us look at something is strange. So I think one more typo out here. I want to define capital J of tau. Let me just go back here to be this function with this. So I want little j of tau minus 744. The constant term will go away. I'll define, it's an important object, so I'm defining it here. I've defined it wrongly. So it has, but this line is correct. J of tau is Q inverse plus 0 plus order. Okay, the constant term is 0. And we'll just call so this generates, it's the normalized generator of the function field on the fundamental domain. What it means is that if you give me any function which is defined on the compactified space or on this itself, then you can it can be written in terms of j of tau as a rational function of j of tau. This is like meromorphic functions. You know that they form a field. Okay, and so j is the generating thing. So, and normalization here means two things. The coefficient of Q inverse is 1, and the 0 constant term is also gone. Okay, so similarly we can discuss for other groups. So this is a definition, it's a technical definition. Let G be a discrete subgroup of SL2R that is commensurable with SL2Z acting on it. If the quotient is a Riemann surface such that, again, the compactification is genus 0, we say that G is a genus 0 group. It's just a definition. And for every genus 0 group, it's known that there is a unique normalized Hauptmodule. So this guy is the main function field, Jg of tau with the same property. Okay, so if you put G equal to gamma, you get this guy. Okay, and that provides an isomorphism between the compactification and the sphere. Okay, and there's yet another connection with the monster. Ogg observed that for all primes that divide the order of the monster, the group gamma 0 p plus is a genus 0 group. Okay, and just another fact. So I'll just say the definition, and so G intersection SL2Z or PSL2Z, they are finite order in each of them. The full group, it should be commensurable. So no, but G need not be, G is not a subgroup of SL2Z. It's a subgroup of SL2R. So for instance, what I have in mind is something like gamma 0 plus, for instance. P plus, we know that this guy is, the Fricke involution is not an SL2Z element. So we need to look inside the bigger. So it could be bigger. Yeah, otherwise it is commensurable. I mean, absolutely. Okay, that's true. Okay, so, oh, okay, we are doing okay. So let's look at the two conjectures before going on to a third construction of modular forms, because we have all the data that we need. Okay? So the first conjecture, which we already saw, that there exists a monster module V, which is graded by some integer m, such that dimension of Vm is the coefficient of Q power m minus 1 in the Fourier expansion of J of tau. Okay? So J of tau, capital J of tau starts with 1 by Q or Q inverse. So V0 would be associated with that. And we know that the coefficient is 1. And so V0 is C. And the next term is not there, the constant term. So V1 is 0. And V2 upwards is are given by dimensions of this. Okay. So for instance, the dimension of V2 is 1 plus the smallest irrep of the monster. Okay. And so now what Thompson did was a little bit more. We can do this for any G belonging to the monster to define something called the Mackay-Thompson series. It's Tg of tau is equal to, so you take some of these things and you do traces by restricting to the subspace Vm and multiply it by q power m minus 1. Okay? And then, for instance, what will happen is that now so this term just is nothing but the character of G in this module Vm. And remember, Vm is it's not an irreducible module of M, it is a reducible one. Okay? But so from our little data, we already know that this should be Q inverse, okay? Because here just 1 came, 1 is just the trivial representation, and all characters are 1. So then, and you get a 0 here, and the next one will be chi1 plus chi2, where I'm just labeling them. The chi1 and 2 are the characters of the 2 smallest irreps of M. Okay. So once we have this kind of data, we can go either to the atlas, and it's a fairly big book, and so if it falls on your leg, you may break your leg. So be careful. But actually, people at GAP are very, very nice. What they have done is they actually have stored all the character tables of the monster, so you can go there. An exercise for you is to actually check what I have written out here. Okay. So what I did is precisely that. Went to GAP. I also have Atlas, but and got these numbers and just plugged these things and did some. I did a few more computations, obviously. I mean, I know more things, and you get a Q series for these guys. So T, and the subscript is the conjugacy class, because this doesn't depend on the value of this depends only on the conjugacy class. So it suffices. So 2A, 2B are again the Atlas labels. Okay. Don't ask why something is called 2A and 2B, please. You ask the guys who wrote the Atlas, they have assigned it. And does GAP always follow Atlas notation for the labeling? Okay. So yeah, so you should be careful sometimes to check if 2 different places have different. But this is the Atlas notation. The second notation, second conjecture, also we know enough now. It says that the Mackay-Thompson series, Tg of tau. So we saw that the idea here is that let's assume conjecture 1 is true. Okay, and then ask what does it mean? What does it imply? And this is what Conway and Norton did. And so they say so the Mackay-Thompson series Tg of tau is a normalized generator of a genus 0 function field arising from the group Hg. So you give me Tg, it's a Hauptmodule for some subgroup Hg that lies between gamma 0n and gamma 0n plus. Remember, that was its normalizer in PSL2R. For some n dividing order of G times GCD of 24 order of G. Okay? So this whole thing boils down to this fact. Sometimes this is easier for me at least. Tg of tau is equal to J8G of tau. Both are normalized. So there is no ambiguity, and this is the statement. Okay? So little bit more structure. M has 194 conjugacy classes, and naively one would think that that we should have 194 conjugacy. Such Mackay-Thompson series. But it turns out that for instance, elements of order 27, there are 2 of them, and they have the same Mackay-Thompson series. Okay, and but Conway and Norton did quite a lot of work. They identified the precise I mean, this conjecture is, as it's written, is very imprecise. It doesn't tell you what is what, but actually Conway-Norton did much, much more. They identified what the precise genus 0 groups are, as well as the required modular forms. And the results were presented via a large number of tables. I mean, it takes a while to even, every column carries a lot of information and a lot of fun working through it. But here's an example, H2b. So that means you take an element which is in the conjugacy class 2b of the monster. And for that, it is just gamma 0, 2. And T2b is ratio of Dedekind eta functions and plus a 20. So, okay, so I'm doing good. So the theorems, they are not conjectures anymore. They are theorems today. The first theorem is due to Frenkel, Lepowski, Muirman. It's not written as a theorem because I think they had to create a huge machinery. So, so it appeared first as an announcement in this. So the first publication is 1984. In 1985, they gave a slightly expanded version, a talk which appeared in a book, in a conference and appeared in a book. And then eventually they wrote a book. Okay, so that appeared in 1988. So it's a long thing, but I have just written a simple. There is a monster module B natural with the properties in conjecture 1. And this natural actually, there is some point they're making with this. They're saying that this is the way you should actually think of the monster through this module. This is the one natural for the monster. The next one is theorem is Borchardt. This is a proper theorem, and this is just Borchardt's theorem. Suppose that V equal to, V is the infinite dimensional graded representation of monster constructed by FLM, which is here. Then for any element G of the monster, the Thompson series, he calls it the Thompson series, but most of us call it now the Mackay-Thompson series. Tg of tau is the Hauptmodule for genus 0 subgroup of SL2R. That is, V satisfies the main conjecture in column and not. Okay, so this is, so these are conjectures. So in this, in my next talk, we will spend some time trying to understand the ideas really which go into this thing, because it's a very technical construction, but interesting what is happens here. This is also interesting, and Borchardt actually introduced a generalization of Lie algebra, of the usual Lie algebras, which he called generalized Cox-Moody algebras, but today we call it Borchardt's Cox-Moody algebra. Okay. So I'll finish in the next 7 minutes with a third construction for modular forms. Okay. So there are, I mean, I kept going back and forth. I mean, in physics, we think of lattice as very, very simple way, but in maths, there is 2-3 ways of doing it. So I will just write, and hopefully I'm not saying anything wrong. Let Q denote a quadratic form in R variables, and further, let Q be, I mean, is a map from ZR to Z, be a positive definite quadratic form taking integral values. So, and we'll be very explicit. Let Qx be this half. Let it be there. Is Aij xi xj, and so you can collect. So the data of this quadratic form can be collected as a R by R symmetric matrix, and with one condition for that Aii are even. So if a matrix is such that it has integral entries, with the diagonal entries being even, we'll call it an even integral matrix. And the quadratic form similarly as even integral. Positive definiteness implies that det A is greater than 0, but many more conditions are there. But det A greater than 0 implies that it's invertible. Okay. So examples, large class, the root lattice of any simply laced Lie algebra with A will be a quadratic form with A given by its Cartan matrix, and you can check that it satisfies. The English is very bad here, but it satisfies. Okay, so to Q, we can associate what is called a Theta series. Okay, so it's very simple. You take all x's which belong to ZR and Q power this particular, and you sum over it. Okay. So now it turns out that this, under certain conditions, is a modular form, and I'm going to state a theorem which is true only if R is even if R is odd, it doesn't mean it doesn't work. You just need more bells and whistles. Okay? So define Q, define the level of Q to be the smallest positive integer n equal to nq, such that NA inverse is even integral. So A is even integral. You're not guaranteed that A inverse will be integral because its determinant can be something. So you'll, right? So you just need to multiply by a suitable factor so that it also be so that it becomes even integral. Even integral, and so that's called the level. And let D be equal to minus 1 power R by 2 determinant of A. Okay. So now the statement here is that theta of Q is a modular form of weight R of gamma 0 nq with some character. So that means there can be some phases going with it. But but other than that, it's like a modular form of weight. So for you, the takeaway here is that the theta series associated with the lattice has weight R by 2, where R is the rank of the lattice. Roughly, there are more things to add to it, but this is what we should consider. Okay. When determinant of A is 1, interesting thing happens. First thing is that A becomes a unimodular lattice. And you remember now A inverse will also be even integral. There's nothing to worry about because there was always, when you're taking the inverse, there's a 1 by determinant of A that's not giving any fractional terms. So the level of that thing is going to be 1, which means it will be a modular form of the full group. Okay? Now comes lattice facts. That is that such, so what we have is a lattice associated with even integral unimodular quadratic form, but that you can show that such lattices are self-dual. And important result is that such lattices occur only when the dimension of R is divisible by 8. Okay? So now we are going to use the full power of the things which we did in the beginning of this lecture, and we're going to see, let's go to 8 dimensions. In 8 dimensions, we are told that there's exactly one self-dual lattice, and that is just the E8 root lattice. Okay, so E8 root lattice has rank 8, so we expect a modular form of weight 4. Okay, but then there's nothing to check it. Theta of E8 better be E4. Because we know that the modular forms of weight at 4 is only 1 and it is given generated by E1. And both, another thing to see here is that in the theta series, the way I've written it, if you put, the point 0 gives 1, so the theta series will always start with 1. And then you get 240q plus order q square. But we can ask, what is this? And if you go back, and so 240 is just the numbers in the root lattice with length. Again, by length, we just mean what the quadratic form evaluates to equals to 2 equals 240. Okay? And this is just nothing but the number of root vectors of E8. Okay? And if you break it up into positive and negative roots, then 120 would be the thing. And 248, if you remember, is the dimension of the Lie algebra. So if you add the Cartan, which is 8, you get 248. Okay. In 16 dimensions, there are only 2. And these are the root lattices of E8, E8 plus direct sub E8 and D16. Both are modular forms of weight 8 on gamma, but there is only one modular form. Both of them start with 1, so both of them have to be equal, and they have to equal E4 square. Because it's again something we saw. Okay? So we get something very interesting, which says that these two theta functions for different lattices are the same. Okay? And this actually, this was the first, Milner used this result to disprove a conjecture of Marquardt's, which says that can you hear the shape of a drum? So that's a complicated question about the spectrum of the Laplacian. So if two different spaces have the same eigenspectrum, I mean, the idea is, can you distinguish two spaces by just their eigenspectrum? And the answer is no. And the first answer came in 16 dimensions because there are two different tori in 16 dimensions whose spectra are given by the same theta function. So continuing this thing, in 24 dimensions, there are many of these guys. There are 24 such lattices that were classified by Niemeyer. The theta series for the 24 Niemeyer lattice will all have weight 12, but now the dimension is 2, which means that they need not all be equal, but some of them might be equal. I mean, this doesn't say anything about that. Okay? But there is a special lattice called the Leech lattice that has no vectors of norm 2. Thus, theta of lambda must be 1 plus 0 times OQ square. Claim. Again, the space is 2 dimensions. We know 2 coefficients. It's fixed. Modularity fixes the whole answer. And it tells you that theta of lambda is this. I mean, I just did some linear algebra. And bingo, I get this thing. And I can also now write what the order Q square term is. It's some 196560 Q square. Okay? Only point to remember is that it is smaller than the smallest dimension of the smallest irrep of the monster. Also, a little bit of games will show you that there is an identity like this. Theta of lambda divided by the discriminant is for both are 12, 12. So, and if you look at the structure, it should have it should be Q inverse, and it should be writable in terms of J, because J is a Hauptmodule. Okay. So you can actually observe that the number of vectors of norm 2 in all the 23 other lattices can be determined by their theta series. Okay, so I'll just just make 2 points and just stop here. So theta E8, we'll look at this again. Theta E8 we saw was E4, but and we got 140. But if you divide by eta power 8, what you observe is, forget this factor of this thing, you observe you get 248. 248 is precisely the dimension of the Lie algebra of E8. Okay? Then if you look at 4124, it can be written. Again, I just did some quick numerology. I just tried to solve this thing. You can see it's written like this. And so it's the sum of the dimensions of this thing. So is there a moonshine for E8? Short answer is yes. And we know why. Because this is a character of the unique representation of the affine Kac-Moody algebra. Okay. And there is another simple fun fact. For some reason you get, not some reason, you get a cube root of J of tau. Because if you cube this, you get J of tau. So I think I'm done for now. Next, do I have anything here? No. Okay, so we will start from this next lecture and see how these kind of objects will come from vertex operator algebra. I must say that the maths audience, you are very polite. By now in physics, Ashok, we would have been asking lots of questions. I'm used to being sort of bombarded with things. People telling me what you're saying is wrong. All that is kind of acceptable in physics. You choose a basis, and I mean, you just have to. Yeah, so I mean, the way I would say it is, okay, I'll show you in a particular way. So suppose, let's say that I have some basis for, say, r power r, and with the inner product, aij, and then the lattice for me will be you can go back and forth. So that I had put some conditions on Aij, and so for instance, non-degeneracy is important so that EIs for 1 to R provide a basis. All those things will work out. But roughly, this is you can go back and forth. It's very important. Yeah. And it's also, I mean, yeah, it's also important for convergence of this series. So suppose you, I mean, you can write theta series for cases which are not Euclidean lattices, but you know, Lorentzian and stuff like that. And there are serious issues with convergence. You need to choose something. You have to make some things for making things convergent and stuff like that. But in these cases,